Assalamu alaikum warahmatullah. Hello and welcome everybody to this video. My name is Maron Fatani, and today we will be talking about antennas and their radiation and all of the formulas that come with it. So in this slides, our reference will be the 8th edition, Applied Electromagnetics by Olabi, and the slides are edited by Dr. Ahmed Omar and Dr. Hussein Atiyah. So the first question that comes to mind, what is an antenna? What do I mean by an antenna? The antenna is basically the bridge that connects signals. Instead of a cable, we are going to send them through air or no medium at all. Um, so to give you an idea of signals that I'm talking about, like radio waves or microwaves, all of these waves that travel through unbounded medium. So to give you a better idea, you can imagine the two people talking through a string and a can, and the string is like the cable, and the open air is where the sound waves travel freely. So we basically are taking the um, signals that is being transmitted through the guided electromagnetic wave, and then the antenna is going to direct this wave into the air. The antenna is a transducer that converts a guided wave propagating an translation line into an electromagnetic wave propagation. There are many examples of antenna, and each example of an antenna is going to give you a different type of different type of wave pattern. So there is thin dipole, biconical dipole, loop, helix, long periodic, parabolic dish, reflector, horn, microstrip, and the list goes on. Now the antenna is a reciprocal device, and what do I mean by reciprocal device? It means that they work the same with whether they are transmitting or whether they are actually receiving electromagnetic wave. So if they are effective at transmitting, let's say, a signal at the X direction, in that direction, then it's also going to be most effective at receiving a signal in that same direction. So that is what is meant by a reciprocal device. Now, to talk about antennas, there are a couple of properties that defines how good an antenna is. And first thing we're going to talk about is the radiation pattern. The radiation pattern means the way the antenna spreads out a signal. It's like if you think of a bottle spray, how it sprays the water, how the antenna actually spreads out the radiation pattern. And then the antenna polarization, which is the orientation of the electric field in the plane wave. And then we also have, that's at the output. At the antenna input impedance, we have the reflection coefficient and the bandwidth. And by bandwidth, I mean the range of frequencies that the antenna can work with or can handle. Okay. Moving forward, we are going to talk about the antenna radiation. We have actually, there are a lot of types of antenna radiation, but I'll first talk about the isotropic antenna radiation, which is it's a hypothetical antenna that radiates equally in all directions, which is this sphere right over here. You can imagine that the antenna actually radiates in all directions equally, which is not possible, not realistic. A more realistic antenna distribution would be this one right here, which is actually produced by, if I go back, it is produced by a horn antenna. So the horn antenna produces this type of radiation or pattern, antenna pattern. The antenna impedance, the antenna impedance is how much resistance the antenna offers to the electrical current. This is basically have to do with the transfer of power from a generator to the antenna when the antenna is used as a transmitter. And also, again, since it's a reciprocal device, when the antenna receives a signal. Now, we go forward with the radiation sources, and we have two types. We have two types of radiation sources, or two categories. We have currents and aperture fields. And what is meant by current is it's like dipole antennas, which we will go, which we're gonna explain in a couple of moments. They're basically time-varying currents following the conducting wires, which give rise to radiated electromagnetic fields. It's like vibrating a string to produce sound. That's an analogy for it. And we have aperture field, the second category, which is used with the horn antenna. Because the electric and magnetic fields across the horn and aperture serve as the sources of the radiated fields. You can think of it like a speaker's diaphragm for creating sound waves. Um, like in like in speakers. And there is also a little concept called far field approximation. So to explain the far field approximation, close to the antenna, the signals are like ripples in a pond. And as you go further, the radiation becomes flatter and flatter, as you can see right here. So imagine this is the pond right over here. If you place a rock and you start seeing the ripples at the pond close to the source, they are going to be curved. But as you go further and further, they're going to appear much, much more flat. So the idea behind far field approximation is to simplify the math. Um, to simplify the math. And the whole process of that is called far field approximation, which we are going to talk about later. So let's not talk about triples in a pond. Let's talk about this transmitting antenna right over here. Antenna, we have the spherical wave being transmitted, but as you go further down this R direction, we have the signal starts to flatten out, kind of. And this line right overhead is the plane wave approximation. Moving forward, we are going to talk at last about the Hertzian dipole, the short Hertzian dipole. Now, the Hertzian dipole is a long string of, not string, a long conductor that has current passing through it and a generator with the property of length L, the whole wire, right over here. It is a very short antenna, and one of its main property is that the wavelength that the antenna is less than 1/5 of the signal's wavelength due to its small size. And the current across it is nearly constant. It's not really constant, but it's nearly constant. And to solve it, it's really not easy to find it isn't easy to solve for this big antenna of length lambda over 2. So what we're going to do is we're going to take a small piece of the antenna, and then we're going to analyze it. And once we analyze that small piece, we can then integrate over the whole um, half-wave dipole antenna, which is what we're going to go through in the following section. So the Hertzian dipole, the short dipole, with the length less than lambda over 50, lambda being the wavelength. What we are trying to do, the goal of this section, is to find the electric and magnetic waves radiated by this wire dipole antenna at a specific point Q on the space. So let's redefine the parameter that we have in this graph. We have the XYZ plane, we have our current going upwards, and then we have the length of the antenna, and then we have theta, phi, and phi is the angle between the X and Y, theta is between the Z and X, and we have the R, which is the radius, and R dash. The radius R is the point from the origin to the point Q, and R dash is the point of any specific small segment of the wire of the antenna until you reach Q. And Q is exactly the point in space that we are trying to define the properties of the electric and magnetic fields. So the electric field radiated outwards from the dipole. We have a couple of formulas that we can um, show. Okay. So firstly, we have the current along the dipole. We have the current multiplied by the cosine omega t, which is a sinusoidal current wave because our generator is also sinusoidal. We have the magnetic vector potential. And then we have S, which is the cross-sectional area of the dipole. And before I said that the R dash is from any point to Q and R is from any point to Q. But because we are dealing with a very short dipole, we can approximate R to R dash to R, which is going to simplify our math. And from Maxwell's equation, we have our magnetic field and electric field. So the radiation is actually controlled by the current distribution, how distributed the current is, because the current is not really constant over um, this whole conductor, this whole antenna along the length L. It actually varies. So this function right over here is called the spherical propagation factor. It accounts for the 1 over r decay of the magnitude with distance, as well as the phase change represented by e to the power of jkr. So with the given current along a dipole, we can calculate A with the direction along the Z multiplied by mu node over 4 pi I node L multiplied by this spherical propagation factor. So we have the electric field is proportional. We can think that our electric field is proportional to the current and the length of the wire and inversely proportional to the radius and the wavelength. And which is exactly the same as with the magnetic field. They are both proportional to the current and the length of the antenna or half-wave dipole antenna and the radius and inversely proportional to the radius and the lambda. So we have this spherical sphere that is going to radiate in an S direction, let's say. This is the radiation source in the S direction. Don't mind all of these lines, they're just to show you the angles at each section of the sphere. Now, very important subject, we have to convert the z to spherical coordinates. So our z hat becomes r hat cos theta minus theta hat sine theta. And once we plug that back into this formula up here, we can get our answer in terms of the in the x, y, z coordinates. After solving for AR, A theta, and A phi, and applying Maxwell's equation, this leads to our final equations for the magnetic field, electric field along R, and electric field theta. We have as I said before, the electric field and magnetic field, they are proportional to I to the current and length, and we have the decaying factor multiplied by sine theta. Now, let's look at this picture and try to analyze just a little bit of what is going on. We can look and find some interesting findings. We have zero radiation, and as the antenna radiates, we can find that there is a lambda, 2 lambda, 3 lambda, 4 lambda. At each of these segments, the antenna again, it just goes outwards like a cone shape. Now, for the far field approximation pattern, um, the radiation pattern looks something like a donut with no radiation directly above or below the antenna. Because as you go far away, as you go further, you won't have any um, radiation pattern vertically above or below it. It's going to be like a donut, only to the right side and left side. So if I think of an analogy, it will be something like a campfire. You're sitting and the fire is going upwards, but the heat is going to the right and left. Uh, it goes outwards horizontally and not vertically. And again, as I said before, to mathematically make these equations a little bit more manageable, we are going to cancel out any squared or any radius that has a power of 2 or more. And using far field approximation, we can then finally find our electric field and magnetic field with these two simple formulas. And you notice that ER just vanished because it is negligible. Once we got rid of both of these, the value becomes extremely small. And then now with the far field approximation, the wave appears as a uniform plane wave, as a line as I showed you before. We have the electromagnetic fields in phase, uh, and their directions are orthogonal to each other, and both fields are proportional to sine theta and independent of phi because of symmetry. Now, um, for the normalized radiation intensity, first we're going to talk about the polarization. Um, the polarization basically is just a background. It determines how the wave oscillates. It is the dipole's orientation. Um, and the radiation intensity, it indicates how strong the radiated signal is in different direction, um, uh, in different directions in the pattern. Of course, it's going to be reference to a normalized intensity for comparison reasons. So we have a couple of formulas here. We have the electric and magnetic fields, which we calculated from before. And we have our average power density, which is the curve of E with the conjugate of H. And if you do the math, you are going to get SR theta is equal to all of this. And finally, we have our average power is S node sine squared theta. Now, the normalized radiation intensity, which is the intensity at a specific place in the pattern, is F theta phi. And it can be simplified as f theta is equal to sine squared theta. And we can also see a couple of observations from these formulas right here. We can see that S max is directly proportional to the current and the length of the antenna. And it's inversely proportional to the radius and the wavelength. So the more the current, the more the length, the more the S max. Now, I want to show you some radiation patterns for teasing dipole. We have F theta, the intensity, which is this formula we got from before. And as you can see here, we have the radiation pattern of our dipole that we talked about before. And F theta, to visualize it, it is the intensity at this point, for example. And it's going to depend on sine theta because at different angles, you get different intensities, as you can see. And if we take a cut, a vertical cut of this, like that, we are going to find that this is the elevation pattern and this is the azimuth pattern. Elevation pattern mean we take a cut in the vertical and azimuth in the horizontal. So if we take a cut on the horizontal, we're going to see this circular donut-like shape with zero radiation in the middle, and it increases as you go outwards, as shown in this figure right here. So no energy is radiated by the short dipole along the direction of the dipole axis. And there is a maximum radiation, F equal 1, occurs in the broadside direction at theta equal 90, because sine 90 is equal to 1. So that's where you get the maximum radiation. And noticeable also is that our intensity does not depend on phi, because phi is the circular the XY angle, and if you look at this figure right here, it's equal, so it doesn't matter at which side in the XY plane it is. Well, what matters is at which side it is from the XZ plane, because as you go upwards, the intensity decreases, but as you go around, the intensity doesn't really change. And that's it for our first section. Now we are going to move on to the next section. We will be out. We'll be talking about the antenna radiation characteristics. So there are 6 things we're going to go through: total radiated power, antenna power, beam dimensions, antenna directivity, radiation efficiency and gain, and antenna radiation and loss resistances. To begin, we are first going to talk about a prerequisite for all of this, and that is the steradian. Now, what is the steradian? We are all familiar with pi, which is equal to 3.4. Okay, and we can find the arc length as r times the theta, which is this whole thing right over here, and the circumference is equal to 2 pi radian. Now take that concept and try to apply it onto a sphere. So the radian basically is the unit of angle where the arc length equals this circle radius. So one full circle is going to equal to 2 pi radians. If you take that same concept and apply it to a sphere, we are going to try to measure the whole sphere circumference, where the arc length of that is going to equal to the radius, which is basically going to be equal to 4 pi steradians. Now, to make this a little bit more easier to absorb, you can think of it like slicing a pizza into angles, and that's for pi radians. But in a steradian, it's like slicing an orange into 3D sections, as you can see right over here. You can imagine this as an orange, you're trying to slice something out of it, and this gradient is going to be first by the curved area, which is equal to r squared. So once gradient is defined as the solid angle with its vertex at the center of the sphere of radius r, that is subtended by a spherical surface area equal to that of a square with each side of length r, if that makes sense. So let's go through the visualization one more. Once radian, where the area is equal to r squared and the radius is equal to r. Now we're going to talk about the total radiated power. In the total radiated power, we have so the definition of a total radiated power first is the energy the antenna sends out into space from the given energy that it has. So it's basically the energy that is being sent out through the antenna. We have the solid angle, the rho associated with the dA. Of course, from now on, most of the time we're going to be dealing with only gradients. So we are going to try to find the power at a specific small segment on the sphere. And using spherical coordinates is going to be r sine theta d theta. This is r d theta. This is the elevation plane, the azimuth plane. And we are going to try to find the area in this very small piece and try to find the power in that specific area. So we're trying to find the average power density in that specific vector, and then find the small area element on the radiation surface. So this whole thing, you can think of it as the S average, or the average power, multiplied by the area, the small differential area of that sphere. Now, the antenna pattern. The meaning of antenna power, antenna pattern, it describes how the power radiated by antenna varies in different directions. So as the antenna has the field of antenna in this pattern, there you can think as in this place we have a different energy than this pattern, than this place, than this place, than this place, than this place. So the power radiated actually varies in different directions. It's not in a constant. This whole pattern doesn't have the same energy as every other point on it. And the 3D representation, this shows the strength in every direction with different colors. So we have the normalized radiation intensity, F theta phi, the directional pattern of energy radiated by an antenna. And this is a 3D plot for the normalized radiation intensity in decibels. So as you can see, in different points, we have different angles, zenith angles and different azimuth angles. In this plot right here, we have different radiation intensity, and so different power. The principal planes, which is the elevation and the azimuthal plane, the elevation plane is also called the theta plane. I've explained this before, and the azimuth plane is the phi plane. Now these are just the different plots that can be used to sketch the power. We have the polar and rectangular plots, and in this plot right here, in the rectangular plot, we have the normalized radiation intensity in decibels, and then we have the x-axis as in the zenith angle, heat in degrees. If you look carefully at this pattern, it actually looks quite similar to the one right over here with all of these small directions, which is also in dB. We're also working always in dB. Now, you noticed something in here, which is beta 1 over 2 at exactly -3, and the small line coming down with theta 1 and theta 2. We're going to explain that in a bit. So we have something called the half power beam width, which is beta equal to theta 1, theta 2 minus theta 1. And this is basically the half power beam width is the angle between two directions where the power actually drops to half its maximum value. So if that was the maximum value, when the power in that direction, in the pattern, in the direction of the pattern becomes half, and half translated in dB becomes -3, and we draw two lines coming down to the angle, and we find the angles of both of these lines. After we minus them, that's going to be our half power beam width. And another concept, which is the null beam width, that's basically the angle between points where no radiation is present. So in these points, there is no radiation, it is 0. The angle where it is null, we don't have any radiation. Now, what is the pattern solid angle? It's a very important concept. The pattern solid angle, it is defined as an equivalent cone over which all radiation of the actual antenna is concentrated with a uniform intensity equal to the maximum direction of pattern. So to explain it in a much, much simpler way, it is the region in space where you can think of it where the antenna radiates most of its energy. So as the antenna has a pattern, where is most of its energy being radiated? And that's the pattern solid angle. And the formula for it, which is this is the represented by this variable rho p. We can find the intensity integrated, which is the normalized radiation intensity integrated across d rho, which is equivalent to sine theta d theta d phi in the spherical coordinates. So the half power beam width it is defined as the angular width of the main lobe between the two angles at which the magnitude is equal to half its peak value. I explained that just now. Now, in this slide, we are trying to, let's say, okay, so for an antenna with a single main lobe pointing in the z direction, we're trying to approximate our beta as the product of half power beam width, because we have the x-axis and the y-axis. If you take a cut in this cone, and you take a cut from the xy cone, and then you take a cut from the negative, the x plane, and then the y plane, we're gonna have beta xz and beta yz, because this pattern could be on the x plane or the y plane. So once you get the beta xz and the beta yz, multiplying them is actually an approximation to the solid pattern, which can be found by just integrating the intensity. Now, we're going to talk about directivity. The definition of the directivity is basically, according to the book, it is defined as the ratio of its maximum normalized radiation intensity to the average value of overall direction. In simpler terms, It is the ratio of the antenna's maximum radiation in a direction, in any direction, to the average radiations in all direction. So we are trying to find the ratio between a specific direction, the maximum radiation in a specific direction, to the average radiation of all the directions. We're trying to find how much is that place, is that, let me find a, how much is a, so how much this place here is concentrated, how directive, how much can the antenna direct our power in a specific place compared to other places, if that makes sense. So if we have, let's try something this way. So if our directivity is high, it means that the antenna focuses energy in that specific direction. It is capable of that. Okay. It's like using a magnifying glass where if you put it in the sun, you can actually focus the light in one place. It is something like that. And we have the formula for directivity, which is equal to F max over F average. And we have F max already equal to 1. And the F average that we can calculate, that we calculated before. And then plugging it all over each other, we're going to get that our directivity is equal to 4 pi over our solid pattern. Now, a quick note here is that for an isotropic antenna, our solid pattern is equal to 4 pi. And so its directivity is going to equal to 1. And that means that it, as we said before, the isotropic antenna can radiate in all places equally. So the directivity is going to be 1 because it is equal in all directions. If it's not 1, if it's different, then the directivity is different. And so since we have the SAV equal to the isotropic, where isotropic is the power density radiated by an isotropic antenna, D represents the ratio of the maximum power density radiated by an antenna to the power density radiated by an isotropic antenna. Both measure the same range R and excited by the same amount of input power, which I explained just now. And again, directivity is most of the time in decibels. It is usually expressed in decibels, which is just 10 log R directivity. Antennas with single main lobe. So for antenna with a single main lobe pointing in the z direction as shown in, it can be approximated as the solid pattern is equal to beta xz, beta yz, which I explained before. And therefore we can find the directivity with a different formula for pi beta xz, beta yz. We're just substituting our values that we got before. Now we're going to solve this nice equation. I'm gonna bring out my draw pencil here. So in this example, the antenna radiation, it's example 9.1 in the book, antenna radiation properties. We're going to determine the radiation of maximum, direction of maximum radiation, the direction of maximum radiation, the pattern solid angle, the directivity, and the half power beam width in the YZ plane for an antenna that radiates only into the upper hemisphere. Now this is very important, only into the upper hemisphere. With a normalized radiation intensity given by F is equal to cosine squared theta. So from this statement that only on the upper hemisphere, what we can do is, usually in this graph, as you can see here, our antenna basically most of the time has a lobe like that to complete it. But in our case, we are going to only account for the upper hemisphere, which is up here. And to account this constraint into math, we can see this right over here. So our F is going to equal to cosine squared theta when theta is between pi over 2 and 0. And our phi, because phi is in that direction, so it doesn't matter. What matters only this direction. So it's from pi over 2 to 0, and phi is from 2 pi to 0. And it is 0 then everywhere else. Now, to find the direction of maximum radiation, we can just take our f theta, which is our cosine squared theta, and see when does it become maximum. And that is when theta is equal to 0. And now moving forward, because at theta is equal to 0, this becomes 1. So this is our maximum. I think it's simple. Moving to equation to B, we are trying to find the pattern solid angle. Again, we derived this formula before. So what we can do is just substitute our f theta phi into the equation, which is basically cosine squared theta. And then we can adjust our integral based on the constraint that we found before of only on the upper hemisphere. So these are our constraints. Adjust our integral. Proceeding to solving cosine squared theta integral, we're going to divide by 3. It's very simple integration. Find the substitute pi over 2 minus 0 into the theta. And then we can do the integration from 2 pi to 0 of our newfound value. And we can get the solid pattern of 2 pi over 3. Extremely simple. Now, continuing, we have C. We are trying to find right now the directivity. The directivity, which we found the formula for before, which is 4 pi over the solid pattern. We already found the solid pattern as from the previous slide as 2 pi over 3. So we just substitute the values. Extremely simple, and we can find our directivity as 6. But if you remember, we said we show directivity in decibels. So we are going to multiply by 10 log 6, and that is our directivity, 7.78 decibels. Now, the half power beam width, we explained before that it's when the power is exactly half. So we're going to try to find the intensity when it's equal to 0.5. So we take our F from before, our F once again, which is cos squared theta, equate it to half, and then square both sides. It's just simple math. Find the inverse of cosine, and you get two values, minus 45 and minus 45. Did 182. You minus them, and that is our half hour beam width right over here. Now, solving example 9.2, which is the directivity of a Cartesian dipole, we can calculate the directivity of a Cartesian dipole using our equation 9.23, and that equation 9.23 is just this one right over here. Now substituting f theta equal to sine squared, this goes inside here, and we have another formula. Quite simple. We can do the integration here like we did in the question before with our cosine squared. So we do the integration of sine cube theta, and we can get 8 pi over 3. We have 4 pi, doesn't change, and we get 1.5. We get 1.5. And in decibels, it is 1.76, 10 log D. Now, radiation efficiency again. Radiation efficiency, according to the book, is the total power transmitted, which is transmitted power supplied to the antenna. We have a couple of important parameters here that we need to look at. We have PT, PRAD, P loss, and our radiation efficiency. Okay. So the radiation efficiency, in simple words, which is right here, it is the fraction of power supplied to the antenna that is actually being radiated. Um, so to map these values, we have here a very simple diagram. Prad is the power actually being radiated. PT, uh, it is the total power being supplied to the antenna. And we have a lot of losses as our total power from our, let's say, battery generator or whatever, or sinusoidal signal. As it transmits power, we have a lot of losses that comes with the transformation to a signal. We have impedance and mismatching losses. We have dielectric losses, conductor losses, polarization mismatch losses, and also um, reflections and heat, which are all basically resistances in the wires itself. So the formula for the radiation efficiency is me, this mu is equal to P rad over PT, the total power radiated over the total power transmitted. It's quite simple. Um, we also have our gain defined by this formula over here, which is basically saying that it is equal to the efficiency multiplied by the directivity. Now, a very important difference between gain and directivity is that the gain accounts for ohmic losses in the antenna material, and the directivity doesn't. So for a lossless antenna, our radiation efficiency is going to be equal to 1, obviously, and our gain is going to equal to the directivity. So you can the antenna gain as the it basically combines the directivity and the efficiency to measure the antenna's performance, like the quality, how good the quality is. Now radiation loss, antenna radiation and loss resistances. So back to some basic electric engineering, we have our impedance, and this is our line impedance at the input. We're basically looking at the resistive components. We have the Rn, the R radiated loss, and R loss. We're looking at losses. So this came from the fact that this is our formula for the power. The total power is equal to the radiated power plus the lost power, which should add up to the total power for the conservation of energy. So the total Rn can be defined as the sum of radiation resistances and a loss resistance R loss. And the radiation resistance, this basically represents the power radiated as electromagnetic magnetic waves. And this loss resistance, this is the power loss due to heat or any material problems, imperfections, not problems. And this is our basic formula. P rad is equal to half I node R squared, and P loss is equal to the same just with R loss. And so the efficiency is going to equal to P rad over PT. We can start substituting the value that we have from before, and we get that we can get the efficiency just by finding the R rad and R loss. Now we're going to end this whole session with the last example, which is 9.3. So we have a 4 centimeter long center field dipole. Let's know the values that we have. We first have our length. and then we have 75 megahertz, and it's used as an antenna at 75 megahertz, so that's our frequency. The antenna wire is made of copper and has a radius of A is equal to 0.4. We have our radius. And from equation 7.92a, loss of wire length L is given by, we have R loss, a formula for R loss. Mu C and rho C are the magnetic permeability and conductivity of the wire, respectively. Now, what is supposed of us is to calculate the radiation resistance and the radiation efficiency of the dipole antenna. The radiation resistance and radiation efficiency, radiation resistance and radiation efficiency, which we talked about right over here. So, wait, I cannot find my mouse. Okay, it's right here. Okay, good. So we're trying to find PRAD, and to do that, we need to start with first finding our lambda, which is simple. We already have the frequency, 75 megahertz. This formula is used to find the lambda. Wavelength, speed of light or frequency, we get 4 meters. And then we're gonna find the wavelength ratio, which is 10 to the power of -2. We're doing that so that we can actually know that this is a short dipole, and we can use this formula right over here. Once we do that, we are trying to actually find the we are going to try to find the PRAD, and that actually is going to depend on that is going to depend on the S max. So I'm going through the steps again. First, we did the wave calculation, and then we found the wavelength ratio, and we confirmed that it is a short dipole. And then we're going to start with the power calculations. So PRAD depends on S max. So if we want to calculate PRAD, we need S max, which is right over here. And the dipole is given. And so we need to start substituting. Our D is equal to 1.5. It is 1.5. And S max, which is the maximum power density, which can be found from the formula right over here, or more precisely 15 pi I naught squared over R squared multiplied by L over lambda squared. So substituting the values into pi rad, we can pi rad, power radiated is going to equal to, just doing calculations and simplifying, we get 40 pi squared multiplied by I squared. Now equating these results to equation 9.33a and then solving for the radiation resistance R rad. Radiated leads to R radiated is equal to 80 pi squared multiplied by the lambda over lambda squared. So we have the R rad is equal to 0.08 ohm. Next we determine the resistance R loss for copper. We can it is given from you can just look it up and you can find 4 pi times 10 to the power -7 and rho C. We can find the R loss as 0.036. Therefore, the radiation efficiency, finally, using the formula right here, we needed the R rad and R loss is going to be 0.08, 0.08 plus 0.0036, which is 0.69. So the dipole efficiency is actually 69% efficient. And a very small note that these parameters are dependent on frequency. So it is important to know the tennis frequency, operating frequency. And that is it. Thank you very much for listening to my explanation. It was a pleasure giving this lesson. I hope you learned something of value, and thank you very much for listening. Appreciate it.